This is Hofstadter's butterfly. It's one of the most remarkable fractal structures in nature, and is a very rare example of an exact solution in quantum mechanics. This very famous plot here shows the allowed energy levels of a two-dimensional flat sheet of electrons under the extreme conditions of an enormous magnetic field. In 1976, Douglas Hofstadter was just a graduate student when he discovered this, at a time so long ago that we didn't even have the word fractal to describe his discovery. By now, Hofstadter's problem has become a rather classic problem in condensed matter physics, so much so that we often ask students to reproduce Hofstadter's calculations in their solid-state physics courses. Today, we have a lot of evidence for Hofstadter's butterfly in real materials. This evidence comes from magnetotransport experiments and compressibility or thermodynamic experiments. These are all experimental probes that are sensitive to the Fermi level state of a material as it changes as a function of, say, magnetic field or carrier density. So these experiments really cleverly leverage the design of artificial lattice materials that are designed through either lithographic patterning techniques or moiré band structure engineering. These artificial lattice materials are designed to have these very, very long wavelength superlattice potentials that admit clear signatures of Hofstadter's butterfly at laboratory scale magnetic fields. So there are many, many examples of this in the literature, many wonderful experiments, but I was a little surprised to find out that today, in 2025, nearly 50 years since Hofstadter's original calculations, we still have never visualized Hofstadter's fractal energy spectrum directly. That is, there are no existing spectroscopic measurements that have resolved Hofstadter bands in a real material. Today, my teammates and I are really excited to share with you a new paper on arXiv where we've solved this issue and made the first observations of Hofstadter bands in a moiré material, namely second magic angle graphene, which we believe is a sort of model platform for these observations. There are a lot of advantages that I'll tell you about in this talk of why we like this material. So using this moiré material, we're able to make some kind of fundamental verifications of some results in Hofstadter's original work. There's this really famous result from Hofstadter's paper that says that at one magnetic flux quantum for Q lattice unit cells, where Q is an integer, the Hofstadter spectrum is very simple. It just has Q Hofstadter subbands. And so this is an example of one of those experiments. At 1/6 flux per unit cell, we saw 6 discrete Hofstadter bands. Moreover, spectroscopic information that's available to the STM is new and different than that information available to previous experiments and gives us new insights, a complementary perspective on the Hofstadter regime. So here's an example of one of those experiments where we did spectroscopy at a series of magnetic fields, and under a nice scaling law, we find that the data collapses onto itself. The Hofstadter bands in this material look very self-similar at these magnetic field strengths as direct signatures of the fractal structure of this spectrum. Finally, spectroscopic tools like the STM are really fantastic at being able to discern the presence, the role, the type of correlation effects that cause correlated electron phases in our materials. And so we use the spectroscopic resolution as a function of all of these parameters to identify that the Hofstadter spectrum in twisted bilayer graphene evolves really dynamically as a function of density. There are Hofstadter bands that split at the Fermi level due to exchange interactions, and interactions among electrons, in fact, actually close topological gaps in the spectrum. So all this will be discussed in this talk. Thank you so much for joining me. My name is Kevin Nuggles. I'm a Pappalardo postdoctoral fellow at MIT, but all of the work I'll be showing today was done while I was still a graduate student at Princeton with Ali Yazdani. So we're going to talk about the Hofstadter butterfly, and I already mentioned that this is a sort of classic problem in condensed matter physics. And to me, that classic nature really stems kind of more broadly from the fact that in quantum mechanics, we have a lot of tools, a lot of approaches for solving systems approximately, for giving proximate solutions to quantum systems, but we have very few exact solutions. And so as physicists, we hold each one of these really near and dear to our hearts. These are often the subject of a lot of our undergraduate coursework in quantum mechanics, where we learn how to solve the behavior of electrons in a periodic potential. So assuming like maybe an atomic lattice. The solutions here look like block waves. These are plane waves that are periodic with a lattice, and the energy spectrum that they emit, the allowed energy states, are continuous. So we get a continuous band of states distinguished by their momenta. We also learn how to solve the behavior of electrons in a homogeneous magnetic field. Here, the solution looks very different. The solutions look like Landau orbits. Semi-classically, they look like these tight cyclotron orbits. And the energy spectrum that they emit is also very different. These are represented by discrete flat bands, which we call Landau levels. So hugely degenerate, macroscopically degenerate Landau levels that are separated by large energy gaps. So highly discontinuous as a function of energy. So in the early days of quantum mechanics, folks were trying to understand how we might be able to merge these two pictures. Maybe I want to understand the behavior of electrons in materials with an atomic lattice, but I also want to know how that material behaves in a magnetic field. So today we have very good approximate solutions at low magnetic fields, effectively corrections to band theory that help us understand how materials behave in magnetic fields. But in the 70s, theoretical physicists found a series of exact solutions, really beautiful solutions at extremely high magnetic fields. The key insight that Douglas Hofstadter had was that at high magnetic fields, there are additional symmetries at hand so that you can solve the system more readily. So these symmetries come from the fact that this problem is dictated by two distinct length scales. The first length scale is, in our problem today, will be the moiré wavelength, which is the unit cell, defines the unit cell of the electrostatic potential. We're talking about twisted bilayer graphene near the second magic angle, and so that moiré wavelength will be roughly 25 nanometers. When I apply a magnetic field, this introduces a second length scale, the region of my device within which one magnetic flux quanta is threaded through the device defines a new wavelength called lambda b. And for arbitrary magnetic fields, these two length scales are incommensurate with one another, which makes the problem very asymmetric. You can see that this system has no translation or rotational symmetries for arbitrary magnetic fields. So the insights from Hofstadter were that at a series of magnetic fields, we should expect that the magnetic length scale and the lattice length scale are actually commensurate with one another. And at these nice conditions, we'll have a new translation symmetry due to this enlarged magnetic unit cell that I depict in these black outlined regions here. So this is a solution at 1 magnetic flux quanta per 4 lattice unit cells, a so-called rational flux per unit cell or flux per unit cell ratio. Here, we'll have a distinct solution that was described to us in Hofstadter's work. This is clearly not the only situation where this is going to happen. We'll have a different solution at 1 flux per 7 unit cells, 1 flux per 4 unit cells, and 1 flux per 3 unit cells. Hofstadter's paper even gives us a prescription for how to handle more complicated fractions, like 2 magnetic flux quanta per 5 lattice unit cells, 5 flux quanta per 17 lattice unit cells. And so we'll have distinct solutions at each one of these rational flux per unit cell ratios. Putting it all together, Hofstadter's paper tells us that we should plot all of the allowed energy levels of this two-dimensional electron gas as a continuous function of magnetic field all the way up to 1 magnetic flux quanta per 1 lattice unit cell. The solutions look really beautiful, as you can see on the computer screen. This is a beautiful fractal energy spectrum, which we now call Hofstadter's butterfly, because it kind of resolves this butterfly feature or this butterfly shape in energy and magnetic field. So there are a couple of features of this plot that I think will be particularly relevant for our experiments today. I think one feature is that the Hofstadter spectrum at 1 magnetic flux quantum per q lattice unit cells, where q is an integer, the spectrum is very simple. It just has q Hofstadter subbands. You can see this from 1 magnetic flux quanta per 2 lattice unit cells. We see 1, 2 Hofstadter bands. On 1 flux per 3 unit cells, we see 1, 2, 3 Hofstadter bands. At 1 flux per 4 unit cells, we see 1, 2, 3, 4, and so on. So this is what's happening at very simple rational flux ratios. At more complicated ratios, like 5 flux quanta per 17 unit cells, the Hofstadter's paper gives us a prescription for generating the spectrum at these complicated fractions recursively. So he identifies some patterns in this spectrum that tell us that we can break the spectrum up into 3 separate components, where the 3 components will look like larger parts of the Hofstadter butterfly, parts near 2/5 and 2/7. So this gives us a feeling for why we're seeing this fractal structure by eye, because it's recursively generated. And small parts of the Hofstadter butterfly are going to look self-similar to larger parts of the Hofstadter butterfly. The continuity that you see by eye of these bands, these Hofstadter bands, is largely in part because of this recursive construction and because the rational numbers are dense in the real numbers. So no matter where I find myself in experiments at what magnetic field strength, I will be arbitrarily close to a rational flux per unit cell ratio where I can exactly solve the system. I have an exact solution. And so to me, this is a really beautiful way to kind of merge these two pictures of band theory and Landau levels, that the spectrum looks at a broad level very continuous, but it's actually made up of discrete Landau levels, discrete Hofstadter bands, if you look at very close, intricate detail of each of these Hofstadter bands. So this is a really beautiful piece of theoretical research, and experimentalists wanted to be able to see this happening in real materials, but this is a tall order for experimentalists, largely because of the scale of fundamental constants in quantum mechanics. So h, the Planck's constant, divided by E, the electric charge. This gives us a sense of what energy scales or what magnetic field scales we should be looking for this physics. And these quantities come out to be 4,100 Tesla square nanometers. This is an enormous magnetic field to be threading through a very small region of my device. And so for almost 3 decades after this proposal, there were no experiments that could probe this physics directly. This is until around 2001, where there was a landmark paper where magnetotransport signatures of Hofstadter's butterfly were uncovered in an artificial lattice material. So this is a really landmark paper in 2001, and where they measured the Hall the longitudinal and Hall conductivity of a Hall bar sample of aluminum gallium arsenide. So this is a semiconductor heterostructure, a very high mobility interface, gives this a nice two-dimensional electron gas. But in addition to this, the authors of this paper, they used lithographic techniques to drill holes in aluminum gallium arsenide, and they evaporated top metallic gate onto the surface, such that as a function of real space, the distance between the gate and the TUDEG changed laterally. But in addition, the places in the semiconductor heterostructure where the Fermi level is pinned was changing as well. So both of these effects cause this large wavelength superlattice potential that is written by man. This is written by the parameters that you use in lithography. And so performing transport experiments on this patterned TUDEG, they measure the longitudinal resistance, which is shown in white, which is kind of changing erratically as a function of magnetic field. It shows more gaps than we should expect in a typical TUDEG. And then the smoking gun signature was that they measured the Hall resistance of their samples as a function of magnetic field. And in a typical two-dimensional electron gas, we should expect this to be either plateaued or monotonically decreasing as a function of increasing magnetic field. So here, that red curve, you can see there are clear regions where there are non-monotonicities, regions where the Hall resistance can't be explained by a typical Landau fan, but can be explained by the intersection between Landau fans produced by the Hofstadter butterfly. So these are signatures of the Hofstadter butterfly at play in this lithographically patterned material. More recently, and in my opinion, maybe a little bit more convincingly, 2D materials have really offered an alternate and clean path towards producing Hofstadter systems. So this work started from 3 simultaneous works. This is Rea Shuri and Pablo Herrera's group at MIT. This is Philip Kim's group when he was still at Columbia, and Andre Geim's group when he at Manchester. So the 3 of these teams, they kind of simultaneously identified that when monolayer or bilayer graphene is aligned to its hexagonal boron nitride substrate, these 2D materials have different lattice constants, and so they present a interference pattern, a moiré pattern that's about 14 nanometers in this material when they're perfectly aligned. And so this produces a very long wavelength superlattice potential. Here's some data from that MIT group where they measured the 2-point conductance of one of those graphene samples aligned to hexagonal boron nitride as a function of carrier density, which is modulated by the gate voltage, and magnetic field, which varies up to about 45 Tesla from a high magnetic field lab experiment. So around charge neutrality, around zero doping, we see features that look a lot like Landau levels that we would see in other graphene devices, but there are regions of the fan where Landau levels emanate from finite filling, which are distinctive signatures of the Hofstadter butterfly at play. So There are many experiments like this that have confirmed these observations and seen Hofstadter's butterfly in a series of moiré materials. All of these experiments, though, are magnetotransport or compressibility experiments. And today I want to try to convince you that spectroscopic probes like the STM can offer a sort of complementary perspective to this problem at hand. So with a spectroscopic probe, we would want to be able to make direct comparisons to Hofstadter's original calculations. Hofstadter predicted a fractal energy spectrum, and so we want to be able to visualize that structure directly. With spectroscopic measurements of the fractal energy spectrum, we might be able to provide some direct evidence for self-similarity of that fractal energy spectrum. And then I mentioned at the top of this talk, but I'll reiterate that spectroscopic tools are really fantastic at being able to identify the presence and the type of correlation effects that modify single particle band structures. And so we'll want to see how correlation effects modify the Hofstadter spectrum in this material. And so we're going to leverage the high energy resolution of the scanning tunneling microscope at millikelvin temperatures. And we're going to perform these experiments of the Hofstadter butterfly, of the Hofstadter spectrum, using the long wavelength moiré potential of twisted bilayer graphene, which is different than the previous materials that I showed you. So twisted bilayer graphene is a homobilayer material, and so by twisting these two sheets of graphene, we can produce very, very long wavelength moiré patterns that are highly homogeneous and admit signatures of Hofstadter's physics at fields as low as 1 Tesla. So before I jump into those magnetic field data sets, I want to tell you a little bit about this platform, some fundamental spectroscopic properties of twisted bilayer graphene near the second magic angle. There was one other study prior to us that probed the transport properties of devices like this. This is from Dima Efesov's group when he was still at ICFO. But there has been largely no other follow-up work on this paper, and so we want to present a nice, clear spectroscopic perspective on this material. So here's an STM topographic image of one of our device regions of the moiré pattern and twisted bilayer graphene. You can see these bright regions in the topograph. We label these as AA sites, where the graphene is locally commensurate with itself, where most of the local density of states is collected. And then there are these interstitial triangular AB or BA regions where the graphene is locally Bernal stacked. So near the second magic angle, single particle calculations predict a dense series of flat electronic bands that are much narrower than nearby angles. So here's a band structure predicted at this twist angle, and I've highlighted in orange a series of 10 flat electronic bands that are very close to charge neutrality. So these will be most relevant to our talk, to our observations, and we'll be looking for these flat electronic bands. So I'll park my tip in the center of an AA site and measure the differential conductance dI/dV, which is proportional to the local density of states in the single particle limit. I'll measure this as a function of the gate voltage Vg, which gives me density resolution, and the sample voltage Vs, which gives me energy resolution, where this center line, 0 energy, is the Fermi level, where a lot of action will be focused. So you can see this spectroscopy, this color map shows a dense series of these sharp peaks and local density of states that each come to the Fermi level and pin for some extended density range for exiting. You can see this really clearly if we look near charge neutrality, where I've put a zoom in on this far right side, where this peak in density of states, it comes to the Fermi level at nu equals +4, 4 electrons per moiré unit cell. It pins for the entire density range until nu equals 0. Before exiting the Fermi level. So each one of these peaks is indicative of a flat electronic state at this angle, and these peaks are much, much sharper as seen at this angle than at nearby angles. So we're using this platform because of a few key advantages, and I think in our paper we distill it down to 2 main advantages of studying the Hofstadter butterfly near the second magic angle. So first main advantage is that second magic angle graphene has a very long wavelength moiré pattern of about 25 nanometers. So this produces a very large superlattice unit cell, which admits clear signatures of Hofstadter's butterfly at very low magnetic fields. At higher magnetic fields, tunneling spectroscopy near the Fermi level tends to be suppressed a lot due to these so-called Coulomb gap features. This is suppression of tunneling at high magnetic fields. And so we want to avoid a lot of this and perform our high resolution spectroscopic measurements at low magnetic fields. So this is really fantastic. If this were the only perspective, though, you might suggest that we should just marginally twist our twisted bilayer graphene to 0.00001 degrees twist angle so that we can access all of Hofstadter's physics at basically zero magnetic field. So this is one perspective, but an alternate perspective is put forward by this other advantage of second magic angle graphene. So near the second magic angle, we have a single particle band structure that's very nice. It's a series of flat bands that are relatively well separated in density. So this will give us a really nice setting for us to make high resolution measurements of how one flat electronic band fractionalizes into discrete Hofstadter subbands. This is really well evidenced from looking at the zero bias conductance in this sample. So this is the differential conductance at the Fermi level as a function of density. And you can see that at integer fillings, 0, 4, 8, 12, 16, these are regions between each of the flat bands, and the zero bias conductance, the Fermi level density of states, is deeply suppressed. There's these deep suppressions of the zero bias conductance, indicating that these flat bands at the second magic angle are relatively well separated, although there is some density of states between them. So this will be a really nice setting for doing so, and at smaller angles, this is not true. The moiré bands are very complicated and highly overlapping. So without further ado, let's jump into the low temperature, high magnetic field data that will be the focus of this talk. So we'll cool down device regions like this from 4 Kelvin down to millikelvin temperatures and apply a magnetic field. And you can see that this flat band in second magic angle graphene has kind of broken apart into what at first looks like a dense series of lambda levels. This is a graphene device, and so we should largely expect lambda levels to be present in these types of devices. But kind of an alternate perspective can be found if we really focus intimately on the Fermi level. So look at the density of states at the Fermi level, which is plotted on the right side. We see that what used to be at high temperatures and zero magnetic field, a single flat electronic band, seems to now have broken apart into 6 even parts in local density of states. So 1, 2, 3, 4, 5, 6. Each one of these parts takes the same amount of gate voltage, and so it contains the same amount of density as resolved by spectroscopy. So this was a little perplexing to us at the time of taking this data, why this flat band is breaking up into 6 equal parts. But we were able to unravel this mystery very quickly on the sample by just looking at our samples topographically. So by looking at the sample regions of interest, we can measure the unit cell area, and I can divide the magnetic field by this unit cell area to get that at this magnetic field, we're very close, very, very close to 1 flux per 6 lattice unit cells, immediately suggesting that what we're seeing is that flat bands near the second magic angle are fractionalizing into discrete Hofstadter subbands. So to further evidence this, we performed some experiments where we changed the magnetic field to a couple of simple flux per unit cell ratios and measured the zero bias conductance. So at 1 flux per 6 unit cells, we saw 6 Hofstadter bands. At 1 flux per 5 unit cells, we saw 5. At 1/4 flux per unit cell, we see 4, and at 1 flux per 3 unit cells, we see 3 Hofstadter subbands, immediately suggesting that this is a really fantastic hypothesis for making our understanding of this system. So I think the experiment that we would really love to do, the idealized experiment, is particularly clear in this setting. So I have a spectroscopic resolution on a sample that's showing the Hofstadter butterfly, and so I immediately want to rush back down to zero magnetic field. I want to send the gate voltage to 0 to send the sample back to charge neutrality. And then with the STM, I'll measure the lambda levels, or the Hofstadter bands, out to arbitrarily large energies, to very, very large energies, and then very, very slowly sweep the magnetic field in order to resolve all of the intricate structure of the fractal energy spectrum directly. So although this would be a really beautiful experiment, a really fantastic experiment, it's a bit idealized, and it's not particularly practical because of how electrons interact with one another in real materials. So this is a bit of a technical point, but I think it's really important. And so I want to spend a bit of time, a second, to describe how interactions affect spectroscopy due to quasi-particle lifetime effects, which affect all spectroscopic measurements. So if I'm measuring in spectroscopy a real material, then I'm trying to measure the energy of a quasi-particle that is strongly interacting with the Fermi sea of electrons from which it came. And so a really common metric that people use to quantify these interactions is the quasi-particle lifetime tau, which gives me generally a sense for about how long will it be until this quasi-particle scatters into a new unoccupied state. So this is a common metric that people use. And you can see from this definition that it is intimately tied to what unoccupied states are available for this quasi-particle to scatter into, which at its core will be energy dependent. So consider for a sec, I'm a quasi-particle at the Fermi level at 0 temperature. Then this quasi-particle can't scatter into any states below the Fermi level because all of those states are occupied, so I'm Pauli-blocked. It also can't scatter into any states above the Fermi level. Although they're unoccupied, this quasi-particle doesn't have any energy to scatter. And so the quasi-particle lifetime of a quasi-particle at the Fermi level at 0 temperature diverges. At higher energies, though, the story is a little bit different. Now I have some energy to scatter with other quasi-particles, and so these scatterings cause a finite quasi-particle lifetime. And at higher and higher energies, I have more configurations for scattering available to me. And so my quasi-particle lifetime will become very, very, very short at higher energies. Because my quasi-particle's lifetime is very short, the uncertainty in that lifetime also becomes very short because all of the lifetime is expected to be near 0. And so Heisenberg would tell me that if I have very, very little uncertainty in the quasi-particle's lifetime, then I'll have a lot of uncertainty in the quasi-particle's energy. This is the real crux of the matter in spectroscopy, is that if I'm trying to measure the energy of a quasi-particle away from the Fermi level, then its energy is broadened by uncertainty relations that cause me to measure many separate values, a broadening of a spectroscopic peak away from the Fermi level. Fermi liquid theory gives me a feeling for how quickly this will happen, that he tells us that the quasi-particle lifetime scales like e squared. And so this actually occurs very quickly as I move away from the Fermi level. Peaks in spectroscopy become broadened with a proportionality factor that will depend on how strong are interactions in my material. So putting this to play, how does this work in twisted bilayer graphene? Here's some experimental data of the differential conductance at charge neutrality in a magnetic field. So at this magnetic field, we should resolve discrete Hofstadter bands, and we can definitely do so right around the Fermi level. You can see these two sharp peaks in the local density of states. But if I move just a little away from the Fermi level, we see this kind of blurred nebulous region of spectroscopy in red and blue. So I claim that there are actually 3 Hofstadter subbands hidden in this kind of nebulous region of spectroscopy, but I think I'd be really hard-pressed to be able to convince you via this data that that's really true. But really, the nice advantage of the sample is that twisted bilayer graphene is gate tunable. And so I can pull electrons out of the sample using the backgate and push the Fermi level into this spectroscopic blob and bring it to the Fermi level. So once it's at the Fermi level, quasi-particle lifetime effects are no longer so detrimental, and I can clearly resolve 3 separate Hofstadter subbands. I can do the same thing. I can add electrons back to the sample using the backgate and push the Fermi level into this blue peak and see 3 separate Hofstadter subbands. And so I think this data really clearly illustrates that we'll need to be able to perform spectroscopic measurements as a function of density and energy simultaneously in order to resolve Hofstadter's butterfly. And this sort of idealized experiment is not really practical, but there's an alternate route to similar data. So putting this all together, we're going to measure spectroscopy as a function of density and energy at a 1/6, 1/5, 1/4, and 1/3 flux per unit cell. And we can see at each one of these fields, there are clearly 6, 5, 4, and 3 distinct discrete Hofstadter bands, verifying some predictions from Hofstadter's paper. There's a bit of more robust version of how to identify Hofstadter bands based on the topological invariance of Hofstadter gaps and via the strata formula, which describes those topological gaps. This is a bit more of a technical approach, but I'll refer you for these details to the manuscript. I won't cover them today. So with this spectroscopic data, we found that there was a lot of information that we could now use to compare to theoretical simulations of local density of states that allowed us to extract some relevant energy scales in twisted bilayer graphene. So working very closely with Michael Shear and Jonah Herzog-Arbeitman and Biao Lian. These are all theorists and friends at Princeton. Together, we came up with a minimal model that we think really nicely describes twisted bilayer graphene near the second magic angle that starts with the Bistritzer-McDonald model. This is a really common model that people use to describe moiré materials. And into this model, we input a series of moiré parameters that we measured topographically, so the twist angle and the strain of our device. To characterize those strain effects, we include these effects as interlayer heterostrain, which acts to reshape the single particle Hofstadter spectrum, although these corrections were very small because we focused on regions that were extremely low strain regions. Finally, we added an additional energy scale to account for interaction effects. This energy scale is a filling-dependent Hartree potential, which accounts for electron-electron Coulomb repulsion, and we found that this was really necessary for being able to explain some very subtle details in our experiment. So using this minimal model with these parameters, we simulate local density of states in an energy and density window that is relevant to our experiments, and we find very excellent agreement between the clusters of Hofstadter bands in some regions of the Hofstadter spectrum, the dominance of very particular Hofstadter gaps, like this Chern 8 gap coming from nu equals +4, and then some of the isolated nature of the Zeroth-Landau level that flanks the spectrum. So we found these kinds of observables looked very comparable between experiment and theory. There were even some very subtle features that appeared at high magnetic fields that we were able to reproduce by this model. So here's an example of that. Here's spectroscopy at 1 flux per 3 unit cells, where from nu equals +4, 4 electrons per unit cell, we see the Chern 0, the Chern -4, and Chern 8 gap, but somehow the Chern 4 gap is absent from this spectrum. Even though it was present at lower magnetic fields, it continuously closed as a function of increasing magnetic field. So even this very subtle feature is reproduced in our model, particularly when including this Hartree potential, suggesting that this model is a minimal and really faithful description of twisted bilayer graphene at the second magic angle. So I want to shift gears a bit and tell you about how we're going to use our spectroscopic resolution to evidence some of the self-similarity of this fractal energy spectrum. Before I jump into that, though, I want to review why we should expect self-similarity, or what this term really means when we talk about fractals more generally. So fractals were first discussed, although not named, by at this time by Mandelbrot in a seminal work in the 60s, where the seminal work is titled "How Long is the Coastline of Britain?" In this work, Mandelbrot says that if we were to measure the coastline of Britain with a very coarse-grained approach, with maybe a yardstick, then we would get one measurement of that coastline. If we were to measure it more fine-grained, maybe with 1 millimeter precision, then we'd be able to measure more of the nooks and crannies, and so we'd get a much longer measurement. But if we were to measure all of the microscopic detail, maybe if we did so with like an STM, then we would it's unclear to him whether or not this length scale is even well defined. It may be arbitrarily long depending on how much detail we measure with. And so what he's really grappling with is that in geometry, sometimes we have situations where geometric patterns show detail to arbitrarily small scales, a definition that we've now applied to this new term called fractals, which was then termed in the 70s or the 80s. Fractals in mathematics are often constructed recursively, which gives us small scale structure that looks like large scale structure of those fractals. And so we call this kind of scale invariance self-similarity, or an expanding symmetry. And this self-similarity is a similarity of the fractal after a discrete dilation or a discrete contraction of that fractal. So here, illustrated for the Sierpinski triangle, is a really good example. After an areal dilation of 4, we see the Sierpinski triangle comes back to itself. And it's clear that if I were to dilate it by 3.76 or 4.29, these are not discrete scaling factors, and so the Sierpinski triangle will not come directly back to itself. It's not mathematically related by these non-integer values. So we're going to try to find signatures of this in Hofstadter's butterfly, and indeed, some of the recursive structure of Hofstadter's butterfly was first indirectly evidenced in magnetotransport experiments. So this is data from Philip Kim's group. They measured the Hall conductance of one of their graphene aligned to boron nitride samples, and they did so as a function of magnetic field and density. So they're focusing particularly around 4 holes per moiré unit cell. And they're doing so because in single particle calculations, this is a region where the spectrum has some features of self-similarity. So this point right here, this energy is equivalent to filling 4 holes per moiré unit cell. And you can see this kind of downward facing triangle of the Hofstadter spectrum near 1 flux per 2 unit cells. Here's a downward facing triangle around 1 flux per 3 unit cells. Downward facing triangle, and sort of infinite descending sequence of downward facing triangles that are all look self-similar to one another near these very simple flux per unit cell ratios of 1 over q. And so they're measuring the Hall conductance as a proxy for what are the band features that are being filled in this system. And they plot it kind of suggestively, not as a function of magnetic field, but as a function of 1 over the magnetic field in a really classic way that we would analyze quantum oscillations in most materials. So you can see the Hall conductance has some recursive features. It has this kind of zigzag feature that's reciprocated at all of these very simple 1 over q flux per unit cell ratios. So these are some excellent signatures of this recursive structure, but we want to evidence this more directly from the spectrum itself. And so we'll measure differential conductance at a series of magnetic fields equivalent to 1/6, 1/5, and 1/4 unit cells, flux per unit cell. And we'll do so around band bottom, around nu equals -4, where we expect some self-similarity of the fractal energy spectrum. These Hofstadter bands, they look somewhat similar by eye, but I think the self-similarity is not particularly apparent. But what we can do is perform a discrete scale transformation. So we'll discretely dilate the data by a linear scaling factor of 1 over b. So we'll plot the density as a function scaled by this factor. This factor actually comes directly from Strata's formula for experts in the audience. Strata's formula tells us that this is how topological gaps should scale. But this factor here as a function of energy is largely an empirical guess, that there was no reason that we should do this a priori. But we do so to the data at these simple flux per unit cell ratios, and we find that the data collapses onto itself to a really remarkable degree, that the data looks really self-similar in many ways. The number of Hofstadter bands at each density, the size of the Hofstadter gaps between Hofstadter bands, the shape of the profile in spectroscopy, and their dispersion as a function of density, they all look very similar in these data sets, suggesting that they're actually mathematically related to one another by some self-similarity. A really important feature of self-similarity, if we want to attribute it back to a fractal nature of the spectrum, is that it's discrete. And so if we look away from these simple flux per unit cell ratios, we should not see any of this physics. And so here's an example of one of those experiments. We probe the Hofstadter spectrum at 5 fluxes per 18 unit cells, a much more complicated fraction. Hofstadter predicts that at these more complicated fractions, the Hofstadter band structure, the number of Hofstadter bands, and the types of gaps, the hierarchy of gaps we should see should be very complicated and much more complicated than we should see at these simple flux per unit cell ratios. So forming the same discrete scaling transformation to the data, we find indeed that there are regions of the spectrum that have additional Hofstadter band splittings and new Hofstadter gaps that appear in the spectrum that are not self-similar to those seen at simple flux per unit cell ratios, suggesting that this self-similarity is in fact discrete. We can do something in the upper flat band as well, so around nu equals +4, where again we suggest from single particle calculations there should be some self-similarity. We perform discrete scalar transformations of the data to find that the data again shows remarkable self-similarity at these simple flux per unit cell ratios. But if we probe away from these simple ratios, we find that there are new topological gaps and new Hofstadter band splittings that are not self-similar to those simple fractional values, again evidencing the discrete nature of this self-similarity. So I want to close out by talking to you about how correlations affect the Hofstadter spectrum. Hofstadter's original calculations were single particle calculations that omitted some of these effects, and so we thought that it was interesting to be able to see how correlations that arise in a magnetic field were able to alter the Hofstadter spectrum. So I showed this data at the very beginning of the talk, this movie. Let me get my pointer out real quick. Yeah, excellent. So this movie shows the spectroscopic measurements that we took at a series of magnetic fields as a continuous function of density here. So this is somewhat equivalent to a low resolution version of Hofstadter's spectrum. There are a couple of features that I really love about this movie. So one is that you'll see Hofstadter bands that when gated to the Fermi level, they'll split and they'll close at the Fermi level due to exchange interactions, due to electron-electron interactions. So we'll look at this band right here. So as I gate it to the Fermi level, it splits. That one splits right there. This is due to exchange interactions that we see in the zeroth lambda level. There's a splitting right there, and it closes at the Fermi level. So I'll have screenshots of that to show it a little bit more discreetly, but I think seeing it in animation is really nice. Another thing I want to point out is actually from this video, you can see really distinctly the effects of quasi-particle lifetime effects. So there's these broadened conductance peaks. Here, let me wait till the movie gets back to the beginning. So this broadened conductance peak that when gated to the Fermi level, it becomes very sharp in conductance. And then when I gate it away from the Fermi level, it becomes very broadened. Yeah. Can I see one more time? So this broadened kind of nebulous region of spectroscopy, as we gate it up to the Fermi level, becomes very sharp, four distinct peaks, and then we gate it away from the Fermi level and it becomes very broadened. So really excellent. Look at this. So these are screenshots of that zeroth lambda level, and these illustrate the kind of odd behavior of the exchange gap that we see near the second magic angle. So here's that gap that's appearing only at the Fermi level. It opens and closes at the Fermi level. And we see this exchange gap at low magnetic fields, like 1.5 Tesla. But kind of perplexingly, as you increase the magnetic field, this gap goes away. It kind of lessens and then is replaced by a peak in the density of states. This is really uncommon for exchange gaps because typically correlation effects dominate at higher magnetic fields. So we'll come back to this. Another kind of perplexing feature of correlations was the observation of a sort of inverted quantum Hall ferromagnetism near the second magic angle. So here's a spectroscopy. Now we're zooming in really, really close around charge neutrality, so within a small gate range around charge neutrality. And we can see this zeroth lambda level peak. It comes to the Fermi level, and then there's this suppressed tunneling around the Fermi level due to that exchange gap. You can see it's not due to the tip because of spectroscopy doesn't have this exchange feature in other Hofstadter bands. So near this low density limit, we see this exchange gap. And then there are additional splittings of the Hofstadter bands around lambda level filling factors +2 and -2 due to quantum Hall ferromagnetism. These are isospin symmetry broken gaps that occur due to correlation effects within the zeroth lambda level. So all of these features are due to correlations, and as we increase the magnetic field, we see them persist to 1.75 Tesla, but increasing the magnetic field further causes them to start to lessen, they get blurry, and then at 3 Tesla, there are no signatures of these correlation effects. The lambda level is effectively featureless, suggesting that all of these signatures have been thwarted by some other mechanism. So this is really perplexing, but it does mirror some of the observations that occurred in graphene on boron nitride under very different experimental conditions. So these are compressibility experiments from the Manchester group that showed that these single particle gaps in the spectrum persist beyond 1 flux per unit cell, but the correlation-driven quantum Hall ferromagnetic gaps, they can be persistent at low fields, and then they can kind of lessen or close as a function of increasing magnetic field. So the reason why this is perplexing is because quantum Hall ferromagnetism is often described as an instability due to the Stoner criterion. And when I increase the magnetic field, the density of states becomes larger within a lambda level. And the interactions between electrons are also increasing. So this typically means that quantum Hall ferromagnetism is stabilized by higher magnetic fields in most lambda level systems. Contrary to this, though, in Hofstadter systems, there's another effect called Hofstadter band broadening effects. So to illustrate this, this is the Hofstadter butterfly as a function of energy and magnetic field calculated for second magic angle graphene. If we focus at higher magnetic fields around 1 flux per 3 unit cells, we can see that the flat band of twisted bilayer graphene is separated into 3 distinct parts here. And so each of these parts has the same density and has a larger bandwidth. But at lower magnetic fields, around 1/6 flux per unit cell, that same flat band of density of states is now split into 6 equal parts. And so they're necessarily much more narrow. And so concomitant with the increase of interaction effects that we'd expect in typical lambda levels is with increasing field is this Hofstadter band broadening effects. As Hofstadter bands merge at higher and higher magnetic fields, their bandwidth becomes larger. And so we can probe this directly with spectroscopy. So measuring the bandwidth of these Hofstadter bands at low magnetic fields, we see they're very sharp, conducive to correlation effects. But if we increase the magnetic field, then we see they get a bit broader, they start to split, and then at higher magnetic fields, they're very broad in spectroscopy, indicating that this is a dominant effect in this Hofstadter system. And this is why we're seeing correlation effects that dominate at low magnetic fields instead of high magnetic fields. So with that, I want to tell you that the main experimental result from this paper was that we're able to experimentally establish several fundamental key properties of Hofstadter systems, including some evidence for the self-similarity of the fractal spectrum, and we're able to uncover the role of correlations in reshaping that spectrum. So I'll end with a bit of outlook. There's a couple of experiments that I'm really excited to see come online in the next maybe a couple of years. So one experiment that I can envision people would be interested in doing with this platform, twisted bilayer graphene near the second magic angle, is to image a series of correlated phases that appear in other moiré platforms. So here is some work from Andrea Young's group at UC Santa Barbara. They have much cleaner devices 5 years after the original discovery using graphite gates, and they're measuring compressibility in their devices up at tens of Tesla, and they see some really exotic quantum phases of matter at high magnetic fields. So there's some symmetry-broken Chern insulators. These are Chern insulators that additionally break rotational and translation symmetries of the moiré lattice, and fractional Chern insulators, which are Chern insulators that have a new topological order with fractionalized quasiparticles. So these are really exotic quantum phases of matter, and we would love to use twisted bilayer graphene as a model platform for being able to image these quantum states and understand their microscopic properties. Although we didn't see any of these states in our current devices, I think this could be a matter of details of the device. So we may need to go to slightly higher magnetic fields or lower temperatures, or maybe slightly less magic angle twist angles. Another perspective is that I really loved how we were able to compare the observables from experiment to theoretical simulations of local density of states in order to discern a minimal model, minimal description for our platform. So this gives us the Hofstadter spectrum gives us a lot of experimental observables to make very close comparisons to theoretical simulations. And so Hofstadter spectroscopy could be used as a really nice tool for understanding moiré materials more broadly. We found that the role of topology and correlations in affecting the Hofstadter butterfly was much more clear at finite magnetic fields than it would be at zero magnetic field. So with that, I'd like to thank you for your time and to thank the people responsible. Today, all the experiments I showed you were performed by Dylan Wong, Myung-Chul Oh, and I. The three of us performed these experiments in the lab of Ali Yazdani. We received help on data analysis from Ryan Lee, and then we received really indispensable theoretical support from Michael Shear, Jonah Herzog-Arbeitman, and Biao Lian, all theorists at Princeton. Thank you very much.